Hello friends, so today we are going to solve questions from E10 Thermodynamics, and today we are going to solve the questions from 2024, and we are going to solve 18 questions which are from the mains, and we are going to solve 2 questions which are from the advanced. So total we are going to solve 20 questions, and this is part 3 for the year 2024. So the first question, it states that 2 moles of monatomic gas and 6 moles of diatomic gas are mixed. Molar specific heat for constant volume of mixture shall be. R is the universal gas constant. So here we have to find out molar specific heat, that is C of V for the mixture. Okay. And we have 2 moles monatomic and 6 moles of diatomic. So we know the standard formula for that C of V for monatomic. So we can write that our for monatomic gas, you can say that C of V, let us call this CV of 1, will be equal to 3 by 2 times R, and number of moles, let us call this N1, which is given as 2. Second gas is our diatomic, so we can write same formula for our diatomic. So we have diatomic, molar specific heat for constant volume, that CV of 2 will be equal to 5 by 2R, and number of moles, let us call this N2, is given to as 6. So we can use for the mixture at constant volume, so we can say molar specific heat of the mixture at constant volume, let us call this as CV mix, and we can write the formula for CV mix. Our CV mix will be equal to, for our first one, N1 multiplied by C of V1 plus N2 C of V2 divided by total number of moles, that is N1 plus N2, and we simply substitute the values. So this will be coming as 2 plus 6 in the denominator, and we get as 2 times 3 by 2 R plus 6 times 5 by 2 R. 2 and 2 goes away and 6 goes by 3. Therefore, in the denominator we are going to get 8, and the numerator it will be 3R and plus 15R, which will be giving us 18R. Therefore, this can be approximately written as 2.25 times R. So we have option number 2 is correct. Two is correct. Next question. It states that if the root mean square velocity of a hydrogen molecule at a given temperature and pressure is 2 km per second, the root mean square velocity of oxygen at the same condition in km per second is. So this is based on directly the formula. We know that the root mean square velocity, that is our Vrms, is equal to 3RT divided by m and its square root, where this m, capital M rather, is our molar mass, T is the absolute temperature, and R is our gas constant. And it is given that it is in same condition. Therefore, for same condition means the temperature and pressure will be same. Okay? Or we can say it will be constant for our hydrogen as well it will be constant for our oxygen. Okay? So we can modify our formula according to our both the cases and write the ratio. We can say our Vrms for our oxygen and Vrms for our hydrogen will be equal to, this comes as 3RT molar mass of oxygen, and we have 3RT and molar mass of hydrogen and its square root. At 3RT cancels out, and this can be written as our molar mass of oxygen and molar mass of hydrogen, which we already know. Okay. Molar mass of hydrogen is about 2 and molar mass of oxygen is about 32 and its square root. So we can write that our Vrms of oxygen will be equal to Vrms for hydrogen multiplied by, this will be coming as 1/16, so that will be 1/4, and Vrms for hydrogen is given to us as 2 km, so this comes as 2 1/4, so this 4 goes by 2 and this will be equal to 0.5 km per second. Okay, so option 2 is correct. Next question. It states that the average kinetic energy of a monatomic molecule is 0.141 electron volt at temperature. So we have to find out the temperature at which the velocity, average velocity is given, and we are given Boltzmann constant is given to us, and that should be 10 to the power minus 23. Okay, this should be in power. And so this is directly based on the formula. So we can say that for we have monatomic gas, so for monatomic average kinetic energy is equal to 3/2 K of B multiplied by T, and this is given to us in terms of electron volt, so we have to convert this into joules. Anyway, we can just equate them both. So we get this as 3/2 K of B multiplied by T is equal to 0.414, and we multiply it by 1.6 into 10 to the power minus 19. And from here we can say we substitute K of B, so this comes as 3/2 multiplied by 1.6 38 into 10 to the power minus 23 multiplied by T is equal to 0.414 into 1.6 into 10 to the power minus 19. So from here we can say that our temperature will be approximately equal to 3200 Kelvin. So option 2 is correct. Is correct. Next question. It says that the total kinetic energy of 1 mole of oxygen at 27 degrees centigrade is, use universal gas constant as 8.31. So we have to find out the total kinetic energy, and for oxygen, which is our diatomic. And we know for diatomic the total kinetic energy, which is our transnational, is our, for our diatomic we are going to use the formula with respect to the degree of freedom, which is 5 in this case. So more or less it is directly based on the formula. So we can say that it is asking for, we know that our oxygen is diatomic and our total kinetic energy will be our, in terms of degree of freedom we can write this as F by 2 nRT, and value of F is 5. Therefore we can say that this will be equal to our 5 by 2 multiplied by number of moles is given as 1, constant is given as 8.31, temperature is 27, so that will be coming as 300. Therefore the solution will be coming close to at 6232.5 joules. So we have option number 3 is correct. Option 3 is correct. Next question. It states that two vessels A and B are of same size and are at same temperature. A contains 1 gram of hydrogen, B contains 1 gram of oxygen. PA and PB are the pressure of the gases in A and B respectively. Then the ratio of PA by PB is. So in this case we are given that there are two vessels which are having same size and they are at the same temperature. Only difference is that they are at the different pressure. Okay. So we are going to start with our ideal gas law and move it from there. So we say our ideal gas law. This gives that PV is equal to nRT, and they are same size, so we can say the volume and temperature will be same for both, same for A as well as B. Therefore we can write that P will be directly proportional to our N, because R is already our constant. And we can use where N is the number of moles. N is our number of moles, and number of moles we can find out for both our A A vessel as well as our B vessel. Okay. So we can say for hydrogen, its molar mass we already know, that is about 2 gram per mole, and its actual mass which is given to us is our 1. Therefore, we can write that the number of moles in our A, because the hydrogen is in vessel A, will be equal to our its actual mass which is given and the molar mass. So this comes as 1 by 2, which will be 0.5 moles. Similarly, we can write for our oxygen. For oxygen, molar mass is about 32 gram per mole, and the given mass of oxygen is our 1. Therefore, number of moles in B vessel, that is our NB, will be equal to given mass of oxygen and molar mass of oxygen, which comes as 1 upon 32. Okay. And we have to find out the pressure, so we can use the relationship that pressure is directly proportional to the number of moles. Therefore, we can say that our pressure in A ratio pressure in B will be equal to number of moles in A and number of moles in B. Number of moles in A is our 0.5, and this is 1 upon 32. So this comes as 32 multiplied by 1 by 2. So this ratio will be coming as our 16. So option 1 is correct. Next question. It states that the temperature of a gas having 2 into 10 to the power 25 molecules per cubic meter at 1.38 atm, given that W of K is, it should be 10 to the power minus 23, okay, where K is our constant. And we need to find out the temperature, number of molecules are given, and its pressure is also given. So we can simply use our ideal gas law and we can use ideal gas law and solve it. So we have that our ideal gas law gives us that a P is equal to N K times T, and where N is our number density. N is our, in this particular formula, N is our number density. Which basically means molecules per meter cube. Okay, so we have to take care that it is not number of okay. Now we simply, because we require to find the temperature, so we can say our temperature will be equal to P upon N times K, and P is given as 1.38 atm, so this comes as 1.38 and 10 to the power 5, and N is given to us as 2 into 10 to the power 25, and constant is given as 1.38 into 10 to the power minus 23. And okay, it's quite easy because 1.38 cancels, so this comes as 0.5. And one second. No, one second. The pressure calculated wrong because pressure is given a atm. I simply multiplied by 10 to the power 5. Actually, it should be multiplied by the Pascal. So we can write this as 1.38 multiplied by this will be 101,325. Now it is correct, and divided by 2 into 10 to the power 25, and we have this as 1.38 into 10 to the power minus 23. Now it's correct. So this 1.38 goes away, and this will be coming as 25 minus 23, that will be 2, and it will be approximately equal to 500 Kelvin. So option 1 is correct. Next question. It states that n moles of polyatomic gas, degree of freedom 6, must be mixed with 2 moles of monatomic gas so that mixture behave as a diatomic gas. The value of n is equal to. So the mixture should be a diatomic. Therefore, we can say that the C of V of the mixture should be equal to 5 by 2 upon 5 by 2 multiplied by R. The rest of the formula is same. Okay. So we are given that the mixture should be our diatomic. Okay, let me write the formula. So we can say that our for mixture we can write that our C of V for our mix will be equal to number of moles in the first one, it's C of V1 plus N2 C of V of 2 divided by total number of moles. And it says that the mixture should be behaving as diatomic. So we said that mixture, it should behave like a diatomic. If it is supposed to behave like a diatomic, therefore we can write that C of V of our mix will be equal to 5 by 2 times R, and we have our polyatomic gas. Therefore we can write that for polyatomic, degree of freedom is given to us 6. Therefore we can write this as our, let us call this as C of V of 1 will be equal to 6 upon 2 times R, which comes as our 3R. Okay, and we have to find out number of moles. So this N1 is equal to capital N, and other gas is a monatomic. So we can say for monatomic, let us suppose it is denoted CFV of 2 will be equal to 3 by 2 times R, and its N2 will be equal to 2 because it is given as 2 moles. We substitute all the into our equation number 1. So you can say from equation 1, C of mixture is 5 by 2 times R is equal to number of moles is capital N multiplied by 3R plus 2 multiplied by 3 by 2R, and total number of moles will be equal to N plus 2. And here R cancels out throughout, 2 goes with 2, so we are left with 5 by 2 is equal to, and this will be 3N plus 3. And N plus 2. So now it is quite simple mathematics. We can just cross multiply it, and from here we get this as 5N plus 10 is equal to 6N plus 6, and we make it left to right, and this gives us 5N and 6N, giving us N will be equal to 4. So we got the number of option number 3 is correct. Is correct. Next question. It states that two thermodynamically processes is shown in figure. The molar heat capacity of process A and B are C of A and C of B. The molar heat capacity of the at constant pressure and constant volume are represented as C of P and C of V respectively. Choose the correct statement. So in this case we can see that there are 5 options, because in the examination in which 2024 there were 4 options and none of them was correct one. So we have added this 5th one so that we are able to find out which will be the option is correct one. So basic PV diagram is given, but it is given in terms of log of P, as well as we are given log of V. And there are 2 processes and both are with heat capacities, molar heat capacity C of A and C of V. So for process A, we can write the equation that for process A, we can write the equation that our log of P will be equal to gamma times log of V, and we can further write it that P is equal to V raised to power gamma, or from here we can say that P V raised to power minus gamma is equal to constant. And we also know, or for our specific heat, molar specific heat for our A, we can write that, okay, still we are, so we can say that for C of A will be equal to C of V plus R upon 1 plus gamma. Okay, let us call this equation number 1. Similarly, we can write for process B also same equations. So we can say for process B, once again we are going to get same equation, that but for process B it is PV raised to power -1 is equal to constant. Okay. And therefore we can say that our C of B will be equal to C of V, and this has R, and gamma is our 1 plus 1, which comes as our C of V and R divided by 2. And now we can easily write out our C of P. C of P will be equal to our C of V plus R, which is a standard formula. So let us call this equation number 2 and this as equation number 3. So if you compare 1, 2 and 3, so you can say from 1, 2 and 3 equation, you can easily see that the C of P will be our highest one, then it comes to our C of B, then it is our C of A, and finally will be our C of B. So therefore option 5 is the correct one. Five is correct. Next question. It states that at what temperature is the RMS velocity of the hydrogen molecule equal to that of oxygen molecule at 47 degree centigrade. So this is based on directly the formula. Only thing is that the RMS velocity of hydrogen is equal to RMS velocity of the oxygen. Okay. So we know that our VRMS, the standard formula is our M3RT and its square root. And we are given that our RMS velocity of our hydrogen is equal to RMS velocity of our oxygen. Therefore, we can write this as our 3R temperature of our hydrogen divided by molar mass of hydrogen square root is equal to 3R temperature of our oxygen and our molar mass of our oxygen and its square root. So here our this 3R and 3R cancels out. Similarly, the square root will be also going away. And from here we get that our temperature of hydrogen oblique mass of hydrogen is equal to temperature of oxygen and molar mass of oxygen. Okay, so we need to find out the temperature of hydrogen. Therefore, we can write that temperature for hydrogen is equal to temperature of oxygen multiplied by molar mass of our hydrogen and molar mass of our oxygen. And all these things we know. The temperature is given as 47 degrees centigrade. So for absolute, that will be 47 plus 273. So we get this as 320 and divided by molar mass of hydrogen is our 2 grams and for oxygen it is our 32. And this 32 goes by 10. So we get this is equal to our 20 Kelvin. So option D is correct. Next question. It states that if 3 moles of monatomic gas, okay, it should be actually, this is copied wrong, so I'll just, when solve it, I'll put it, is mixed with 2 moles of diatomic gas, the value of adiabatic component gamma for the mixture is. So we have to find the adiabatic component for our mixture. And so we know the standard formula for our adiabatic component mixture. So we can say for gamma for our mixture will be equal to our C of P for our mixture and C of V of our mixture, and our C of V for our mixture will be equal to, we have for first gas, that is of N1, and it is C of 1 plus second gas, it's C of V2 divided by N1 plus N2. We are going to find out the C of V, then we can easily find out C of P also, because that is only plus R. So we substitute it, we get this as our C of V for our mix will be equal to, we are having a monatomic gas. Okay, let me write it separately. So first is our monatomic, and for monatomic we know, let us call this as F1, degree of freedom is 3, therefore we get the C of V1 will be equal to 3 by 2 times R, and number of moles, that is of N1, is given to us as 3, and second gas is our diatomic, so we can say our F2 will be equal to 5, its C of V2 will be equal to 5 by 2 times R, and number of moles is given as 2. Now we can find out our C of V of mix. So we can say C of V of our mix will be equal to, N1 is our 3 multiplied by 3 by 2R plus N2 is 2 multiplied by 5 by 2R and divided by total number of moles, that is our 3 plus 2, and 2 goes with 2, and this comes as 9 by 2, and it will be 10, so that will be 19, and this comes as 19R, and it will be 6 divided by 12, 3 to 5 multiplied by 2 will be equal to 10. So this is C of V of mix, and now we can find out our C of P of mix. C of P of our mix will be equal to C of V of mix plus R. So this comes as 19R plus 10 and plus R, giving us 29R divided by 10. So now we can just use the relationship that our gamma of mix will be equal to C of P of mix and divided by C of V of our mix, which is equal to 19R divided by 10, 29R divided by 10. 10, R and R goes away. So this comes as our, sorry, I have written reverse. That should be equal to actually 29, and this will be 19. So we get this as 29 upon 19, and it is given the fraction, so this will be approximately equal to 1.1956. I think it should be approximately 1.5. So option number 3 is correct. Next question. It states that a gas mixture consists of 8 moles of argon and 6 moles of oxygen at temperature T, neglecting all vibrational modes. The total internal energy of the system is. So we have to find out the total energy of the system, and it is said that all the vibrational modes are to be neglected. So then it is quite straightforward. We are going to start with our argon, which is monatomic. So we have argon, which is our monatomic. And for monatomic, we know that our degree of freedom is our 3, and its internal energy, let us suppose we call this as U argon, will be equal to F by 2 nRT, which is a standard formula, and we substitute, we get this as our U of argon will be equal to 3 upon 2, number of moles are given as 8, and multiply by RT. So this 8 goes by 4, so we get this as about 12 times RT. And argon, next is our oxygen. Same thing we are going to repeat for oxygen also. So we have our oxygen, which is our diatomic. And for diatomic, there is no vibrational. Okay, you can say no vibrational modes. So therefore we can say value of F is equal to 5. Therefore we can write that our internal energy for our oxygen will be equal to 5 by 2, number of moles are given as 6 times our RT, and we have this goes by 3, so we get from here 15 times RT. Total will be individual summation. So we can say total internal energy that is U will be equal to internal energy of argon plus internal energy of oxygen, and U is equal to, this is about 12 plus 15, giving us 27 times RT. So option 3 is correct. Is correct. Next question. It states that two conductors have the same resistance at 0 degree centigrade, but their temperature coefficient of resistances are alpha 1 and alpha 2. The respective temperatures coefficient of their series and parallel combination are nearly. So we have two conductors and we have to find out their net temperature coefficient when they are connected in series as well as in parallel. So we know that let us assume, because we have two conductors, so we can say let R1 and R2, these are the resistance of their respective conductors at temperature T, okay, and T degree centigrade. Therefore, we can write that our R1 will be equal to our R0 1 plus alpha 1 T, and we have R2 is equal to our R0 1 plus alpha 2 times T. Okay, so we got the relationship between our temperature dependent resistances, which is standard formula for us. Now these are connected in series as well in parallel. So let us start with series. So you can say for series combination, let us call this as equivalent is given as our RS. So our RS will be equal to R1 plus R2. Okay. And for RS also we can write this as RS naught 1 plus alpha S multiplied by T. And we substitute the respectively for each. So we get this as our RS naught 1 plus alpha S T will be equal to R naught 1 plus alpha 1 T plus R naught 1 plus alpha 2 T. And here we have to remember that our RS naught will be equal to R naught plus R naught, which is our twice R naught. So we substitute it here and we get this as twice R naught plus twice R naught, and we have this as 1 plus alpha S T is equal to, we are going to just open our right side, so we get this as R naught plus this will be our alpha 1 T times of R naught plus R naught plus alpha 2 times T times our R naught, and this R naught and R naught we can take as twice R naught. So we get this as twice R naught 1 plus alpha T is equal to twice R naught, and from other side we can take as common, which is R naught times T, giving us alpha plus alpha 2. And let me open the left side, and on the left side I'm going to get this as twice R naught plus alpha T multiplied by twice R naught, and here our this twice R naught cancels out, and we will be left with only twice R naught times alpha S T is equal to R naught T alpha 1 plus alpha 2, and here this T and T, R naught and R naught cancel. Now we get that our for series it will be equal to alpha 1 plus alpha 2 divided by 2. So this is our for series combination, the net coefficient. Okay. Temperature coefficient. Now they are connected in parallel. Same process, but we are going to do it for parallel now. Okay. So we can say for parallel combination, let us suppose this is our Rp, and we can write this as our Rp naught 1 plus alpha p times T. And also for parallel combination, we can say that our Rp will be equal to net resistance R1 R2 R1 plus R2. We simply substitute their respective equations. We get this as Rp naught 1 plus alpha p times T is equal to, and so in the numerator it will be product of both. So we get this as our R naught 1 plus alpha T1 R naught 1 plus alpha 2 multiplied by T. In the denominator it will be addition. So R naught 1 plus alpha times T plus R naught 1 plus alpha 2 T. And we can also say that our Rp naught will be equal to R naught multiplied by R naught and R naught plus R naught, which gives us R naught by 2. Therefore, we substitute it here and we get this as our R naught by 2, we have 1 plus alpha p T, and in the numerator we are going to product, so this is square 1 plus alpha t, alpha 1 t multiplied by 1 plus alpha 2 t, and in the denominator we can take R naught as common, so this will be coming as 2 plus alpha 1 alpha 2 times t, and our this R naught goes by square and this R naught goes by here. So we are left with only 1 plus alpha pt divided by 2 is equal to, and we open the numerator, so we get this as our 1 plus alpha 1 t plus 1 plus alpha 1 t, and this will be our alpha 2 t plus alpha 1 alpha 2 times t, and in the denominator it will be 2 plus alpha 1 plus alpha 2 times t. Okay, and this will be square. Okay, and we have to can use a approximation that agar alpha 1 and alpha 2 are very small, so their product will be also very small, so we can just neglect it. So we are going to neglect this part, and we get this as 1 plus alpha pt divided by 2 is equal to 1 plus alpha 1 plus alpha 2 t, and denominator we get this as our, we can take as common as 2, this will becomes 1 plus alpha 1 plus alpha 2 divided by 2 times t and bracket. Now we are going to use binomial theorem on the right side only, so we get this will be equal to 1 plus alpha 1 plus alpha 2 times T, and 2 we can test with this. So this comes as our 1 plus alpha 1 plus alpha 2 times T divided by 2 and whole raised to power minus 1. So we open it binomially and we get this as our 1 plus alpha 1 plus alpha 2 times T and divided by 2, and we get this as 1 minus alpha 1 plus alpha 2 times T divided by 2, and higher order terms we are going to neglect it. Now we simply multiply it inside and we get this as 1 by 2, and we are left with, so we get this as 1 plus alpha 1 alpha 2 times T, and this will be minus, and this 2 is common, and minus alpha 1 plus alpha 2 times T divided by 2, and this will be minus alpha 1 plus alpha 2 whole square T square divided by 2. And once again we can neglect this square, so we get this as 1 by 2 times, this will be equal to, let me write the left side also. On the left side we were left with only 1 by 2, 1 plus alpha p times T is equal to 1 by 2, and this we can solve. This will be our 1 by 2, 2 is LCM, so this will be coming as 1 by 2, 1 plus 1 by 2 alpha 1 plus alpha 2 times T, and here this 2 and 2 cancels out, and this 1 and also 1 will be going away. So quite simple now. So we get this as alpha, okay, let me write this here. So this is 1 plus T is equal to 1 by 2 alpha 1 plus alpha 2 times T, and this is a plus 1. So here 1 1, this T and T also, so we get the same. That is for parallel also, the coefficient will be alpha 1 plus alpha 2 divided by 2. So in the both cases it is same. So we have our option A is correct. So in case of parallel we have to do much of the approximations, we have to take care of that. So we can say option A is correct. Next question. It states that the pressure and the volume of an ideal gas are related as P multiplied by V raised to power 3 by 2 is equal to K, where K is any constant. The work done when the gas is taken from the state A having P1 V1 T1 to state B P2 V2 T2 is. So in this case we are given that P raised to power some power is equal to constant. Okay. So we can use a general formula for that. We know that if we have an equation for P V raised to power n, which is equal to some constant, and from here we can say that the work done, that is suppose that is W, will be equal to P2 V2 minus P1 V1 divided by 1 minus n. Okay. So in this particular case the value of n is equal to 3, because we are given that PV raised power, sorry, not 3 but 3 by 2. 3 by 2 is equal to some constant. So you can say value of N is equal to 3 by 2. So we simply substitute it. We get the work done W is equal to P2V2 minus P1V1 1 minus 3 by 2. So this gives us, this will be minus 1 by 2, and minus 1 by 2 will be giving us work done is equal to twice. So we get P1V1 minus P2V2. So option 1 is correct. Yes, option 1 is correct. Next question. It states that a diatomic gas gamma 1.4 does 200 joule of work when it is expanded isobarically. The heat given to the gas in the process is. So we have isobaric, which means pressure is our constant. Okay. So we can write the formula that for isobaric, pressure is constant. Therefore, work done that is our W will be equal to P times delta V, or we can write in terms of ideal gas equation, that is NR delta T. And it is isobaric, so we can use our C of P. So we can say our C of P will be equal to gamma times R divided by gamma minus 1. Gamma is given to us, that is our 1.4 times R, and this comes as 1.4 minus 1, which gives us 0.4, and this will be 3.5 times R. Therefore, we can say that our work done is given to us. We have to find out the heat. And for C of P, we can write that our heat, that is our Q, will be equal to N C of P multiplied by delta T. And okay, so we need to solve this part also. Okay, let me write it here. Work done, I can say that my W is equal to NR times delta T. So from here I can say my delta T will be equal to W upon N times R. Therefore, Q is equal to N C of P multiplied by W upon N times R. Here N and N goes away, and we can substitute C of P. C of P was our 3.5 times R. Work done is given to us as 200, and this comes as our R. So here R and R cancels out, so this will be coming as 35 divided by 10, so this will be 35 70 700. So we get that our Q is equal to 700 joules. So option 4 is correct. Next question. states that a 0.08 kg air is heated at constant volume through 5 degrees centigrade. The specific heat of air at constant volume is 0.17 and 1 joule is given as 4.8 per calorie. The change in internal energy is approximately equal to. So we have to find out change in internal energy, and that is our constant volume. So we can use the formula directly. We know that our change in internal energy, and that is at constant volume, which will be equal to our delta of U will be equal to our m C of V multiplied by delta T, and C of V is given to us as 0.7, so we convert into joule per kg. Therefore we can write that our C of V was given to us 0.77 and multiply by 4.18, and this is kilocalorie, so it will be our multiply by 10 to the power 3, which will be coming as 710.6. Now we can just substitute it. We get this as delta of U will be equal to m is 0.08, 710.6, and heated at a constant volume through a temperature of 5 degrees centigrade, and multiply by 5. So we get this delta U will be equal to approximately 284.24 joules. So option 3 is correct. Is correct. Next question. It states that during an adiabatic process, the pressure of a gas is found to be proportional to the cube of absolute temperature. The ratio of C of P to C of V for the gas is. So it says that pressure is cube of the temperature. So we can say that our pressure P is proportional to cube of the temperature, and we have to find out the C of P to C of V, means we have to find out the gamma. That is our C of P upon C of V. This we have to find out, and the process is adiabatic. So we can say for adiabatic process, we know that our PV raised to power gamma is equal to constant, and we are given that P is proportional to T cube. So from here we can say that P is equal to K times T cube, where K is any constant. Okay, we can say that K is any constant, and we can use our ideal gas law. You can say for ideal gas law, we can write that PV is equal to nRT, or from here we can write that V is equal to nRT divided by P, and we know that our P is K times T cube. Therefore we get that the volume V is equal to nRT, and this is K times T cube, and this T goes by square, so we are left with this as our nR K T square. And from here also we can write, because our K is constant, N is constant, R is constant, so we can say V is proportional to T raised to power minus 2. So we can use in the adiabatic process that the product is equal to constant, and so we can say, let me write it here. So we are given that PV gamma is equal to constant. So we know that our P is proportional to our T cube. So this comes as our T cube, and V we found out our T raised to power minus 2, and this whole raised to power gamma, this is equal to our constant. One second. Yeah, we can write. And therefore we can frame an equation which gives us that our 3 minus 2 gamma will be equal to 0, which gives us the gamma is equal to 3 by 2. So option number D is correct. Next question. It states that a thermodynamic system is taken from a original state A to an intermediate state B by a linear process as shown in the figure. Its volume is then reduced to original value from B to C by an isobaric process. The total work done by the gas from A to B and B to C would be. So we have to find out the work done gas from A to B and B to C. And here we can use that so we have this as our this will be our area in a triangle, and okay, so this will be half into base and height. So we have to find out the work done. So I think so we can say that our work done will be equal to area of triangle ABC, and that will be equal to over half into base into height. So we can say this will be equal to over half, and change will be our volume will be 7 minus 3, that is 4, and that will be 8000 minus 4000, giving us 4000. And so this will be our goes by 2, and it will be coming as our 8000. One second, there is some Okay, so this is given in dyne per meter square, centimeter square, sorry. So let me convert it and then we can solve it. And this will be Newton per meter, and this will be 2 into okay, we have 2 units here. Yes, got it. So we can write this will be equal to over 10 raised to power minus 2, and this comes as 10 raised to power minus 4, and this will be our centimeter, and 10 raised to power 2 minus 2, and for 1 second, 10 raised to power minus 4, and let me do it properly. So we can write this will be equal to over and we have 2000. It will be as 2000. Let me calculate separately. So we can say hmm, so let me so we can say work done for AB will be equal to over half, and this comes as our this will be 4, and $8,000 plus 6,000, and this will be dian per let us do it by the basic one, otherwise it is tricky. So we can see the work done, which is our W is equal to P times delta V, or we can also say it as a area under the PV curve. And we are given that so we can cause area under the curve, or AB will be this entire portion, because for AB this will be the entire area in the curve. So we can say for our WAB will be equal to our half, and this will be our 8000 plus 4000 times the our this will be 4, and we can write that our WAB will be equal to this will be about 24,000, and it says that from B to C. And okay, so let us convert this. This comes as our 10 raised to power minus 5 and 10 raised to power minus 4 meter square. Okay. And this will be now Newton. So we get this will be equal to over 2400 Newton meter. So meter square. Okay. Now we come to our BC. Our BC is our basically pressure is constant, so we can just directly use our P delta V. So we get this as our P is our 4000 multiplied by this comes as 7 minus 3, and which will be giving us 16,000, and that will once again 10 raised to power minus 5 Newton and 10 raised to power minus 4 meter square, and once again this will be giving me WBC is equal to 1600. Okay, and this will be 3 minus 7. So this will be minus and this will be also minus. So we get the total work will be equal to WAB plus WBC, and we get this as 2400 minus 1600, giving us 800 joules. So we have our option 1 is correct. Okay. So in this case we have both formula, because the pressure is constant for our BC, so we use P delta V, and for AB we can use our area under the curve. Okay. So we have option 1 is correct. Next question. It states that in the given figure represent two isobaric processes for the same mass of an ideal gas. So we have to find out the relationship between the pressure. So we are given VT diagram, and we have to find out what will be the relationship between the respective pressures. So we are going to start with our ideal gas law, and we know that for ideal gas we have PV is equal to nRT. So from here we can write that a volume will be equal to nRP times T, and therefore from here we can write that the slope will be equal to our nR upon P. N and R both are constant, so therefore we can write that the slope is inversely proportional to our P. Okay. And therefore from here we can write that, or from the figure we can say that slope of 2 is greater than slope of 1. Therefore we can say that our P2 is less than our P1. And if possible we can also say that volume is inversely proportional to our pressure, because for constant, so if this T is constant, so this is our V2 and this is our V1. Okay. And from this equation, I think this can also work. So we can say that our V is equal to nR upon P multiplied by T, and if we, for a particular value of T, this T will be constant, so we can say volume is inversely proportional to our pressure. Therefore our V2 is inversely proportional to our P2, and our V1 is inversely proportional to our P1. So if we write the ratio, V2 upon V1 is equal to 1 upon P2, 1 upon P1, which gives us that P1 upon P2, and from the graph we know that our V2 is greater than V1, or we can say V2 upon V1 is greater than 1. Therefore, we substitute it here, we get that P1 upon P2 is greater than 1. Therefore, we can say that our P1 is greater than P2. This way we can also solve it. So we know that P1 is greater than P2. So we have option of 4 is correct. Is correct. So this is a different method or different approach, we can use it. Next question. This was asked in the 2024 advance. Previous questions which we did, 18 questions, were all from the mains. And it states that the specific heat of a substance is the temperature dependent and is given by the formula C is equal to K times T, where K is a constant of a suitable dimension in SI units and T is the absolute temperature. If the heat required to raise the temperature of 1 kg of substance from minus 73 degrees centigrade to 27 degrees centigrade is N times K, then the value of N is. And here okay, so we have to find out the heat required to raise the temperature. So we know that our heat required, which is our Q, is equal to integration of T1 to T2 C times dt. C is given as K times T, and T1 and T2 we already know, and these are in absolute, so we can say that our T1 will be equal to our minus 73. So let me, T1 will be equal to minus 73 plus 273, giving us 200 Kelvin, and T2 will be equal to 27 plus 273, giving us 300 Kelvin. So we can this as 200, 300, and C we know is K times T and dt. Now it is simple integration. K is our constant, so this comes as T square upon 2, 200 to 300, and this comes as K upon 2. This will be 300 square minus 200 square, that will be equal to our 9 and 4. So that will be our 50,000, and this will be K times 25,000, and we are given that this is equal to N times K. So we get that the value of N is equal to, value of N will be equal to 25,000. So value of N is 25,000. Next question. It was also asked in 2024 advance, and it states that 1 mole of monatomic ideal gas undergoes a cyclic process JKLMJ as shown in PT diagram. 1 mole of monatomic ideal gas undergoes the cyclic process. Match the quantities mentioned in list 1 with their values in list 2 and choose the correct option. R is the gas constant. So basically we have to find out work done, change internal energy and heat given. And okay, for different processes mj and jk, kl, and work done for a complete cycle. So let's write the coordinates or respective pressure and temperature for each point. So we start with J. So we have our J is equal to our P naught, T naught. We have our K, and K is our P naught, 3 T naught. And we have our L, which is our 2 P naught, 3 T naught. And we have our M, which is our 2 P naught and T naught. And respectively, we can find out the volume for each point, and for that we are going to use our ideal gas law. We are going to use ideal gas law, which gives us that the PV is equal to nRT. N is 1, so we can say that our volume is equal to RT divided by pressure P. So we can find out the volume for each point. So we can say V for J point will be equal to R times T naught divided by P naught. And similarly, V for K will be equal to our, this is our temperature is our 3R naught. So this comes as 3R T naught upon P naught. For our L, we can say this will be our 3R T naught and twice P naught. And finally for our M, we can say this will be our R T naught and twice P naught. And all this we can write in terms of our J also, okay, because our J is R T naught over P naught. Okay, so this is our T naught. So we can say that our V of K will be equal to 3 times V of J. V of L will be equal to 3 times V of J, and V of M is equal to 1 by 2 V of J. And let's now identify the processes. So our from J to K, pressure is constant, so that will be isobaric. From K to L, it will be temperature constant, thermal. And then once again, okay, so we are going to have only two processes, isobaric and isothermal. They are going to switch with each other. Therefore, we can say that we are going to have isobaric process, and the isobaric process will be our from J to K. And other one will be, because here the pressure is our P naught, which is constant, and other one will be from L to M, which is our pressure is our twice P naught. And then we will have isothermal, and isothermal will be our from K to L, temperature is 3 T naught, and finally we have M to J, and pressure, temperature is T naught. And okay, so let's find out option P, that is work done in the complete cycle, complete process. So we start with option P, which is work done in complete cycle, as it is, because we know that our change in internal energy for a cyclic process is equal to 0. Therefore, we can say that our Q net will be equal to W net. Okay. And we can find out the work done for each process. Okay. So let's find out work done for our JK, W JK. So this get our P delta V, so this is P naught, and we get this as Vk minus Vj, and we get this as our P naught 3 times Vj minus Vj. So we can write that Wjk will be equal to 2 times P naught and Vj, but this Vj we can write in terms of our ideal gas law, that will be R T naught upon P naught, because we have already, this is our Vj, R T naught upon P naught. So here this P naught and P naught cancel out, so this comes as our 2R times T naught. And next is our WKL will be equal to, this is our isothermal, so we can say that will be equal to nRT natural log of our VL upon Vk, and we can write this R times 3 T naught natural log of, this will be over 3 by 2 times Vj, and this comes as 3 times Vj, and so we get our WKL will be equal to 3R T naught, and at this Vj 3 and 3 cancels out, so this will be coming as natural log of 1 by 2, and that will be minus natural log of 2, giving us minus 3R T naught natural log of 2. And next is our WKL LM, which is also isobaric, so that will be P times delta V, and P is our twice V naught, and we get this as our Vm minus VL, which gives us twice P naught. Vm is our Vj by 2 minus 3 by 2 times Vj, and we get this as WLM is equal to twice P naught, and this will be coming as minus of Vj. We substitute V of J, so this gets twice P naught minus multiply by R T naught divided by P naught. P naught and P naught cancel out, and this comes as minus 2R T naught. And finally is our work done from M to J. Once again it's isothermal, so this we get R T naught natural log of V of J and V of M. We get this as R T naught natural log of V of J. V of M is our 1 by 2 V of J. This V of J cancels out, so we get this as Wmj will be equal to R T naught and natural log of 2. So we got all the work done. So finally W net will be equal to work done because of Jk plus work done KL, work done Lm plus work done over Lj. Sorry, not Lj but Mj. And we substitute them and add them. So we get this as our Jk is twice R naught minus twice T R naught and minus 3R T naught natural log of 2 plus R T naught natural log of 2, and is 2 and cancel out 1 second. It's 2 and minus 2. So we get that our W net will be equal to minus of 2 R T naught natural log of 2. So we get our work done. Complete cycle is minus 2 R T naught natural log of 2. So P goes by 4. So we get from here that P goes to 4. Next is our change in internal energy in the process Gk. Okay. So we have our option Q, that the change in internal energy, we know that is our delta U is equal to N of C of V multiplied by delta T, which will be our 3 by 2 R times delta T. And we can substitute it of delta T. We get this as delta of U is equal to 3 by 2 times R, and delta T we have to find it for J and K. Okay, so this will be T of K minus T of J. So this will be T of K minus T of J, giving us 3 by 2 3 T naught minus T naught. Therefore delta U for our Kj will be equal to 3 by 2 R multiplied by 2 T naught, and here 2 and 2 cancels out, so this comes as 3 R T naught. So we have 3 R T naught, so option 3 goes to our Q, so Q goes to 3. And next is our heat. So we have option R, and it says that our for heat in the process KL, and KL process is our isothermal. So isothermal, we know that its internal energy of KL will be equal to 0, and from first law we know that our heat is equal to internal energy plus work done. Internal energy is 0, so this comes as work done for a path our KL, and for KL we already know that it is equal to minus 3R T naught natural log of 2. Okay. And so Q is equal to minus 3R naught natural log of 2, minus 3R naught natural log of 2, so it goes to our 5, so R goes to 5. And last is our change internal energy in the MJ. Option S. And MJ, okay, MJ is isothermal, so change will be equal to 0. Okay, so we know that our MJ, this is our isothermal, therefore change internal energy MJ will be equal to 0. So we get that our S goes to 2. So we have P4, this and this, and we have Q as 3, so option B is correct. So this gives us S goes to 2. So we get option B is correct. B is correct. So this completes all the 20 questions from the year 2024, out of which we did 18 from the mains and 2 were from the advanced. So this completes all the 20 questions. Thank you.